Hello, I'm Juliette Moncel. I'm a postdoctoral researcher at Chalmers University of Technology in Gothenburg in Sweden with Janine Spletswesser. And one of my research interests is quantum thermodynamics applied to electronic transport. And so this poster is about geometric energy transport and refrigeration with driven quantum dots. So quantum dots are so you have a semiconducting island connecting to electronic reservoirs, and here it's the energy picture. So your electrons are trapped here in the dot. You can put up to 2 electrons, one spin up, one spin down, because we are looking at this really simple model of a single level. And it's connected to here a left and the right reservoir that can have different temperatures. And so because they are electronic reservoirs, they have a temperature and a chemical potential. And here, this is the energy distribution of the electrons in the reservoir. And then these electrons from the reservoir, they can tunnel in and out, and you get some current through the quantum dots, depending on where is the level of the dot compared to the chemical potentials of the reservoirs. And what we have studied is what happens when you drive several of these parameters. You see there are many parameters here. We can take 2, drive them slowly, compared to the electron tunneling, and see what happens. And that's interesting, first for a spectroscopy, because it tells us how, what are the characteristics of this device. And it gives us new insight because we have been looking at AC driving. So typically these devices are studied with just a steady state current without changing the parameters. So we get new insight from driving, and also we are looking at energy transport while charge transport is more studied. And this is also interesting for thermodynamics. Because by periodically modulating the parameter, we are actually implementing some cycle like in a heat engine. So in the last part of the poster, we are looking at refrigeration. So we modulate the parameters, so in particular the tunnel rates. So we allow or not the electrons to tunnel in and out of the reservoirs. And we change also the position of the level, and with that, we are able to implement a refrigerator. And also, what's interesting in this system is that we are taking into account the electron-electron interaction in the dot. So I told you we can put up to 2 electrons in the dot. So if we want to put a first one on this level, we need an energy epsilon. But if we want to put a second one, we need to pay some extra energy U because of the electron-electron repulsion, the Coulomb repulsion. And so what we've done is to do an analytical approach based on the fact that we are in a slow driving limit. So we look only up to the first order in the driving speed. So that's how we get this expansion, and we cut at the first order. And we use, on top of that, a specific symmetry, which is called fermionic duality, which is quite recent and developed in Janine Spletswesser's group. And with that, we get some insightful analytical formulas that help us understand better what's going on in the transport. So to go really briefly, the nice thing about the slow driving limit is that the first order contribution is fully geometrical, so it doesn't depend on the driving speeds and the specific shape in the phase space of how I change the parameters. All that matters is in a sense the area of the driving cycle. So with that, we looked at different cases when we were driving different parameters. And we compared charge transport and energy transport. So it's the first order correction to the steady state transport for the energy here and for the charge. And as you can see, it doesn't happen in the same places. So this x and y axis corresponds to different parameters. So here, this is the energy of the level here. And here, the bias voltage, so what's the difference between the 2 chemical potentials between the 2 reservoirs. And what we also looked at is what happens if instead of having a standard Coulomb repulsion, we have instead attractive on-site interaction, which means that the dots want to have 2 electrons in. So there is some effect of electron pairing, and this gives a really different, if you compare those two, really different features because of this special 2-particle resonance. And so here we were able to see what's the impact of electron-electron interaction on the transport. And then using this, we were able also to identify interesting points to operate a refrigerator. So yes, the idea is to start here with only electron able to come in from the cold reservoir here. And then we lower the energy level because you see this energy level is too high, so the electrons can't come in. But if we lower the level here, now they can tunnel in from the cold reservoir. And then we close the tunnel barrier on the side of the cold reservoir and open on the hot one. And we lift the level, and then the electron tunnel out in the hot. So we transported both charge and energy from the cold part to the hot part. So it's the opposite way to like the standard. If we had just these 2 reservoirs and not doing the modulation, we would only have heat flow from the hot to the cold. And so we can characterize this with the heat flow that's going from the cold reservoir into the dot, and the work we pay to change the energy of the dot and compute the efficiency. And we are able to compare it to Carnot efficiency. And also we looked at, so we saw that we could get up to 15% of Carnot efficiency in some cases, which is already quite good because we are not driving infinitely slowly. And also, we were able to obtain some simplified expression of this efficiency in the limit where there is no temperature difference between the 2 reservoirs. And this formula is interesting because it depends mostly on steady-state transport characteristics of the quantum dots, and of course on the driving speed omega and like how and the driving amplitudes, but mostly on the Seebeck energy of the dot. Also, what we were able to see is that the attractive and repulsive electron-electron interaction in the dot give rise to different advantages and drawbacks. So, for instance, we get a larger efficiency with the repulsive interaction. We get a larger efficiency because the work cost is less. However, with the attractive interaction, we are able to operate with a larger temperature bias. So here, this axis is how large the temperature difference is between the 2 contacts. And it's not that much. I mean, it's very small, but still we can go farther to larger temperature biases here. And that's because the attractive interaction suppresses the detrimental steady-state heat flow from hot to cold in the dot. Yes, this study really told us what's the key difference between repulsive interaction and attractive interaction, and to see what's the role of strong interaction in quantum dots when doing thermodynamics, but also just spectroscopy of the system.